All right, so let's jump into it. So chapter 1, introductory concepts. There's a list of a lot of things, like we're going to talk about some applications to kind of get you excited. Why do we study this topic? And what are the major themes? Balance of energy, mass, and entropy is second law, and etc. So instead of going through that list, let me just say there's a long list and jump into it. There are power plants located in the city. In the southeast side of town, there's a power plant called the Spruce Power Plant. They have units 1 and 2. It's owned by CPS. CPS Energy used to be City Public Service. It's municipally owned utility. That means the city of San Antonio owns CPS Energy. That means you, the citizen of the city of San Antonio, are owning those. You control them. A lot of other utilities are not municipally owned in the state of Texas, but Austin is, San Antonio is, Houston, no, Dallas-Fort Worth, no. Those are private utilities that serve customers and provide electricity and gas. This is a power plant that burns coal and produces electricity, and it's right now feeding the lights in this room and the air conditioning in campus. How does it work? That's the study of this type of class. You burn something, coal, to make a fireball, to get a lot of heat, to transfer that energy out, to put it into a fluid. The fluid goes into a loop from a boiler to a steam turbine, to a condenser, to a pump. We're going to study all those components. And it turns a shaft to drive an electric generator, to make electricity, put it out on the grid, and it's distributed. They have not only Spruce Unit 1 and 2, they also have some gas-fired plants. And if anybody drives on I-10 toward Houston, CPS Energy about a year and a half ago acquired the combined cycle power plants that you could see off of the interstate I-10 right by Seguin. They built them maybe 15 years ago. They were privately owned, but then they were for sale and CPS bought them. And that burns natural gas in a gas turbine to turn a generator shaft to make electricity. And also the residual heat after going through the gas turbines warm enough to put it through a heat exchanger to boil water, to then put steam through another steam turbine. So it's a combined cycle power plant. I'm not trying to overload you. I'm just saying there's a lot of mechanical engineers that have worked for CPS running this equipment, graduated from this program, or other mechanical engineering programs in the state of Texas. They need to know how these pieces of equipment work, and this class is really the bedrock. It's all about thermodynamics. Thermal, like heat, dynamics, make it move. Burn something to turn something. And energy conversion, converting it to a form like electrical, which people want and use in their homes. We also will study the basics for the power system that propels aircraft. Here's a older aircraft. It's run by these engines which are turboprops. There's not that many turboprop engines out there. There's turbofan. There's a lot of turbofan engines, a lot of just jet engines. Don't disturb me, please. And in town, there's a company, Standard Aero. Some of you may get a co-op or engineering summer internship or other things. A number of students have worked at Standard Aero where they overhaul these engines, the T56 turboprops. There's 4 of them here. There's been a lot of aircraft, aviation industry in San Antonio. I mean, not as much maybe as Dallas or up in different cities like Boeing is in Seattle. But surprisingly, there's quite a few companies that are specializing in aircraft-related industries in San Antonio. So we understand the power cycle. This is just an image of a not a condensing unit. Yeah, it's a condensing unit outside your house for air conditioning systems. Do you recognize it? Provides the air conditioning for residential homes, something that you may be familiar with. We understand how the vapor compression refrigeration cycle works to provide air conditioning. And how is that related to companies? Well, in Houston, It's a headquarters for which major manufacturer? Goodman Manufacturing. They don't put a lot of publicity out. They don't have a lot of billboards, but they sell a lot of products in the city and throughout the nation. They have, I think, 15 or 20% residential market share for air conditioning systems. There's also Trane Manufacturing. Anybody from around the Tyler, Longview area of the state? Trane has a manufacturing plant. I know some UTSA grads that are working up there, successful engineers on staff working for Trane. There's a company that's been in town since the 1880s. Now they've had to adapt. They didn't make air conditioning systems in the 1880s. Anybody heard of Friedrich? It's the Cadillac window units. It still is. It's the premier, how do they call that? It's window air conditioning systems. I forgot the name for it, but they're located out, they used to be more on the south or the east side of town. Their headquarters is now by the airport. Unfortunately, about 15 years ago, where did they move all their manufacturing? To Mexico. Well, hopefully that gives you some sense of the many applications of thermodynamics. What we have to do now is just go through and talk about how do we analyze these systems? What do we do? Well, you have a thermodynamic system. Somebody says, I need to do some calculations, make an analysis. You have to clearly identify the system. What is it? It's the focus of the study. Either it's the fixed quantity of matter that you're interested in studying, or it's the fixed region in space that you're interested in studying. That's what you choose for the analysis. That's a thermodynamic system. You could have a system being, here's a pump, and I have inlet to the pump and outlet to the pump, and you might want to put the dashed line indicating an enclosure around that pump, and then that dashed line is the boundary of the system, and what's inside is the focus of the study, what's happening with the pump. For this pump, you may have a shaft, rotating shaft, providing power, mechanical energy to that pump, and the purpose of the pump is to ingest some, let's say, fluid at relatively low pressure and kick it out at high pressure. That's the purpose of the pump. You could also have a turbine. This would be a region in space that's the focus of the study. Maybe you have a piston that can move in a cylinder, and the system would most likely be the substance that's trapped. Oh, you may open a valve and let some new fluid in or out, but for a part of the cycle, as that piston may move back and forth, it may be that it's closed and there's no open valve, hence it's a closed system, and your focus is on that fixed amount of mass who may be at one time be like that, and then at a later time actually have been compressed to a smaller volume. So we focus on that quantity of matter. There's another example of a control volume, a nozzle. What's the purpose of the nozzle? Well, the nozzle, you let in some flow and it goes out here. Do you already have any intuition on a nozzle? Have you any experience with a nozzle? What's the purpose of a nozzle? Like, what's the purpose of a pump? We're going to talk about the purpose of the turbine. Talk about the purpose of a piston cylinder moving back and forth, reciprocating type of engine or compressor. But a nozzle, what it does is it tries to kick it out at high speed. The speed out is greater than the speed in. This would be the inlet V1. And you think about speed, speed's related to the kinetic energy, isn't it? The kinetic energy out would be high compared to the kinetic energy coming in. That's the purpose of a nozzle. And there's a lot of nozzles out there in application. Because inside of, let's say, a steam turbine, you want to get the steam to go really fast, shoot it towards some moving blades, and as it hits those moving blades, induce a torque on a rotating shaft. And so you'll see these nozzles, or may not look like this type of nozzle, but there definitely are passageways in which the cross-sectional area decreases and the speed goes way up. All right. Just like in physics and chemistry, we know that matter is made up of individual little molecules, and they're just banging against each other. And if there's a wall over there, they're banging against that solid. But there's so many of them in such a small space. How many of them? Well, think about air. Molecules, about 2 times 10 to the 16 air molecules in a cubic millimeter of space at, let's say, this room temperature, around 25 degrees C, and one room pressure, 1 atm pressure. That's a lot of air molecules. And so even though we know that all of matter is made up of molecules, we just sort of introduce the continuum assumption where we neglect that nature of the material and we treat it as being continuous. Talk about continuous density, continuous property of pressure, temperature. Well, we talk about properties. What is a property? There's some examples of properties. You could talk about the mass of the system, the volume of the system, the temperature of the system, the pressure of the system. Those are examples, but the property is just simply something that quantifies its current state. Is it large? May have a large volume. Is it heavy? Maybe have a high mass. Is it under high pressure? Maybe it's wanting to expand into a low pressure region. Or is it hot? Does it have a high temperature? So properties help us characterize the current state of the system. And the system state can change, and it's reflected by changes in values of the properties. I don't think all this is very difficult, is it? Nah. Some properties we describe as being intensive. Some we describe as being extensive. Say, I don't think this is all that important. Well, do me a favor. Just kind of commit it to memory here. Just try and say, okay, this is something new. There's 2 types of properties, intensive or extensive properties. Well, what's the difference? It depends on whether or not the property depends on the size or the extent of the system. Think about a system like this, and I think about a property that goes for the whole system. What's the easy one? Temperature, right? Temperature. So let's say I make a little diagram, and this is our room in here, and the temperature everywhere in the room is approximately, 22 degrees C. All right. Here's a question. If I cut that room in half, I have the top half and I have the bottom half. Is the temperature in the top half 11 degrees C and the temperature in the bottom half 11 degrees C? No, that doesn't make sense. Let's do this. Let's say the same room, and I'm talking about another property. Let's say there's a mass of air in the entire room of 4 kilograms. If I cut it in half, would it make sense to talk about the mass in the top half to be 2 kilograms and the bottom half 2 kilograms? Something's different about these properties. Can you see that? One doesn't depend on the size or the extent. I could cut it in half and have the same value of the property. That's an intensive property. So temperature is intensive. Okay? Mass is extensive. How about volume? Volume, intensive or extensive? Volume is extensive. Now, let's do this one. Weight. Let's jump to weight. Weight. I know that I didn't say there were 2 kilograms. I said there were 20 newtons of air in this room. I know you don't like newtons for weight, but that's consistent. It's true. And I say, now take half of the room. Is there 10 newtons of weight of air in the room and 10 over here? So is weight extensive or intensive? Let's call it extensive. How about pressure? 1 atm pressure, 1 atmosphere pressure. Pressure is intensive. Okay. Now, remind me, what was density? Let's talk about mass density. Mass density. What symbol do we like to use for mass density? Rho, Greek symbol rho? What would the density be? What are the typical SI units for density? I want to know the density of water. Tell me the density of water. Oh, it's 1,000 kilograms per meter cubed, right? So it's something like kilograms per meter cubed. Is density the ratio of mass divided by volume? Is that what the definition of density is? It's just the ratio of mass divided by... Is mass a property? Sure. Is volume a property? Sure. We just talked about mass being extensive, volume being extensive, but this is kind of tricky. I have a new property, which is just the ratio of two other properties. It's called density. Is density intensive or extensive? Density is intensive. But density is the ratio of two extensive properties. I know. Often what you can do, if you want to talk about an intensive property, which is our preferred property in thermodynamics, we would like to talk about intensive properties. Then what we can do is just start to look to make a ratio of something that it's extensive, and it'll turn it into an intensive. So hold that thought, but we'll build on that later. So we talk about the state of the system. Think about the system being the gas that's trapped in a piston cylinder apparatus. And I would say, oh, it's at this state where the volume is 3 cubic meter, where the temperature is 300 Kelvin, where the pressure is 200 kilopascal. That all makes sense. And I'm describing the current state of the system by specifying values for these properties. What happens? The system undergoes a change to a new state, state 2. We started at state 1. We might call that the initial state. This is the final state. What happens between the two? What is that called? A process. Yeah, a process. And now the volume could have increased. The temperature could have increased. And the pressure could have stayed the same. Let's play with your intuition a little bit. What has to be happening between state 1 and state 2 if I really have a gas? And it starts at 3 cubic meter volume and it goes to 4 cubic meter volume. It starts at 300 Kelvin and it goes to 400 Kelvin. What happens? What's happening to the temperature? It's going up. Can you tell me just what do you suspect is happening to that gas during the process? There's a heat transfer in. There's a heat transfer into that gas during the process. That's the most logical explanation for why that happened. Why didn't the pressure go up? Well, maybe it was just the right expansion with the right amount of heat transfer to get the temperature increase and the volume increase till the pressure didn't change. The pressure didn't change. All right. Equilibrium, we're going to talk a lot about equilibrium because the states that we're interested in are in equilibrium states. So the two at this point are simply mechanical equilibrium and thermal equilibrium. If I have something in mechanical equilibrium, think about a force balance. It's balanced in force. In statics, you had force balances all the time. A thermal equilibrium, temperature. What about phase equilibrium? Well, then if I have a bucket or a container with liquid and vapor together and it's in phase equilibrium, then I'm not going to have a net transfer from liquid to vapor and vapor back to liquid. There won't be, if I just wait with time, there won't be, after the end of the time, more vapor and less liquid. It'll be an equilibrium. Now, as it's sitting there, molecules are coming out of the liquid and going to vapor, and molecules are going out of the vapor and into the liquid, but they're balanced in equilibrium. How about chemical? Well, you may have something that wants to react, and it reacts such that it gets to a state of chemical equilibrium. These are Thermo 2 topics. The next class. These are Thermo 1 topics this class. So don't worry too much about phase and chemical equilibrium. Next class. Pressure volume diagrams. What is pressure? A property. What is volume? A property. And we like to make property diagrams. So often, the easiest one is the pressure volume diagram. You could put volume on either axis and pressure on either axis, but it's common to put the volume on the x-axis, maybe in meter cubed units, And the pressure on the y-axis, maybe in kilopascal or atmospheres or bar or some units for pressure. And if I took and I said, this is my initial state right here, state 1, and this is my final state, state 2, and I don't really need to know the details of how it got from state 1 to state 2. It could go along that path for the process, or it could have gone along that path for the process. But either way, can you describe a little bit about what happened to pressure during the process, 1 to 2? What happened to the pressure? It decreased. What about the volume? Increased. It's not that hard. This class is not that hard. So what you do is often you put and line up underneath the PV diagram a piston cylinder. And you put the face of the piston such that it lines up. And so at state 1, where is the piston? Right there. What would be the volume at state 1? Well, it would be the cross-sectional area of that cylinder, which would be pi diameter squared over 4, or if you like to work with pi r squared, radius or diameter, either one you want to work with, but that's the cross-sectional area, isn't it? Times some sort of distance this way. Maybe you call that x1. Wouldn't the volume 1 be equal to area cross-section times x1? Is that the... Yeah. And then what happened? Well, the piston moved back. And now the piston's at this location, which is called x2. And the volume 2 is equal to the same cross-sectional area. I'm not changing the diameter or the radius of the piston, times x2. Sometimes you'll hear me say the diameter of the cylinder, sometimes the diameter of the piston. If there's no blow-by between them, what's the difference? Negligible. One's got to fit inside the other, but you put a little ring in there to seal it, and it's the same. So we don't go a big distinction between the smaller diameter of the piston that needs to fit into the slightly larger diameter of the cylinder. They're the same diameter. Make sense? All right. So somebody says this diagram. Where's state 1? Right there. Where it's going that direction to state 2. Describe that process. How constant pressure, but the volume's decreasing, so it's like compressing it. Constant pressure compression. You say, how can that be? Well, it's pretty tricky. You've got to cool it while you're doing it, basically. That's what you have to do. Because if you're going to start to compress a gas, it's going to want to get hot. So you'll have to cool it a lot to keep it from getting hot, and then make it cold so the pressure stays low. All right. What about this one? The volume's constant. And what happens to the pressure? Going up. How is that going to happen? Think about a liquid now. Here it was easy to think about a gas. Think about a liquid. I have a liquid water and a piston cylinder apparatus. I try to move the piston. What's going to happen? Is it easy to compress liquid water? It's essentially incompressible. So as I try to push it, the volume doesn't change, but the pressure goes way up. Okay, I'm trying to help you. You could have a process like this for some cases, right? Liquid water, where you're trying to pressurize it. All right, what about this case? What's happening to both pressure and volume? Decreasing pressure and increasing. It's expanding. It's expanding. All right, from the perspective of that piston that started here and goes to there, the gas that's trapped is pushing back on that piston, isn't it? It's going an F of force on that piston. That force on that piston is equal to, on the face of the piston, the gas exerts a force on the face of the piston, right? That force is equal to either pressure times area, or pressure over area, or area over pressure. Which one? Think about it for a minute. I'm talking about this pressure at state 1, that volume at state 1, but remember we related the volume to the cross-sectional area of the piston times that location. So this is the area that I'm talking about, that area cross-sectional. I dropped the C up here. I could put the C there, C there, C there. You know, it's related to the radius of the piston or diameter of the piston. So which one is true? This one, or this one? The force that the gas exerts on the face of the piston is either P times A, P over A, or A over P. P times A. Think about the units. Didn't we just say pressure was newtons per meter squared, something like that? Or we're going to talk more about pressure, sorry. And then you multiply by area. Isn't that force? Or maybe I said that pressure was force per unit area. So force is area times pressure. Okay. So what happens to the force that the piston feels? Force at state 1, force at state 2. Is it going up or down? Going down. And what do we remember from mechanics? What is the integral of f dx? Got it. Work. You go from state 1 to state 2, 1 to 2. That's why we're interested in gases trapped in piston cylinders and they're going this way and that way, compressing, expanding, is because it's related to the work. It's a boundary work. Does integral f dx make sense? If I put an A right there and an A over there, did I change the equation? I just put A over A. What is F over A equal to? Pressure. What is A times dx? Hey, volume was A times x. What is A times dx? D volume. It's how the small volume changes. So instead of to calculating the work by an integral f dx, we can calculate in thermodynamics integral p dv. Sorry, sometimes I'll put a little hash mark through that v to say this is not velocity, this is volume. And sometimes I just leave it out, sorry. Right? I try to be consistent, but I know I'm inconsistent at times. V can stand for volume, V can stand for velocity, hence sometimes we put a little v with this to say that's the volume, not velocity. Okay, so the work is the integral p dv. The area under that curve is the work. What work? The work that the gas did pushing back the face of the piston. That piston with the little rod, what do they call that rod that then goes to the crank, offset of the crank? Connecting rod to the crankshaft. And there you go. You got a reciprocating engine, either for a compressor or maybe an internal combustion engine, which is burning some fuel, making a hot fireball and expanding, pushing it back, and it's like a gasoline or diesel engine. All right. Did I say that we like PV diagrams in this class? We really do. Yeah, we like them. So get used to them and it'll be easy. It's easy. All right. Somebody says if that piston's moving quite quickly, couldn't I have something like the pressure in one area and the pressure in the other area different? I mean, think about it. How many people have ever been around a motorcycle and they're revving that engine, right? You may own a motorcycle. What's your red line on your engine? How many RPM is red line on the engines, motorcycle engines that you may run? 12,000 RPM. That piston's going very, very, very fast, up and down, up and down, up and down. 12,000 revolutions in a minute, right? That's fast. You might think that because it's going so fast, compressing, expanding like that, that the pressure may not be uniform throughout the gas. But even in an internal combustion engine going at 12,000 RPM, it behaves as if you could immediately stop it, the pressure would be uniform everywhere through the system. There's not much of a pressure difference where if you thought about it moving so fast in compression, you might think that the pressure's high here and low there, wouldn't you? But even in a very fast engine, where you're moving a gas, compressing an ideal gas like air with a little fuel in it, it behaves as a quasi-equilibrium compression process, meaning that it's an equilibrium at every point along the way. It's just slightly out of balance so that it can actually have some motion, movement. So when we talk about that PV diagram, those are a sequence of quasi-equilibrium states which allow us to compute the integral of PdV to get the work. Otherwise, it would be a very difficult problem if the pressure was higher here and lower there. It would be like, forget it, we're not doing it in this class. That's too hard. All right. Cycle. That engine is running in a cycle. A lot of our machinery runs in cycles. We may analyze it ramping up to get to the cycle, but most of the time we spend analyzing systems that are run in a cycle. And so what about a cycle? Let's go to our favorite diagram, pressure volume diagram. Let's just say I start state 1 here. Can you describe the pressure and the volume at state 1? Low pressure, large volume. What do you think I'm going to do to it? Compress it or expand it? Compress it. If I compress it, which way is the volume going to go? That way. What's the way is the pressure going to go? Going to go up some. Let's say I get to this state. That's state 2. Let's say I do something to go to state 3. What happened from state 2 to state 3? Some sort of like combustion. Yeah, you're getting ahead of yourself, but that's great that you have some intuition of what happened. Constant volume, pressure went way up. Somebody dumped a lot of heat in there. How do you dump a lot of heat in it? Probably burned some fuel. Combustion. Then what happened? Maybe you go this way. 3 to 4. What are you doing there? It's expanding. And now from 3 to 4, you want to get back to close this loop, close it, make it a cycle. Just the opposite of 2 to 3 was heating, dump a lot of heat in. What are you going to do here from 4 back to 1? Throw a lot of heat out, cool it. You're exactly right. That's a cycle. We can analyze systems that behave like that. Somebody says, I have a cycle that does this. Pressure, volume. We're going to do this from 1 to 2. We'll do this out to 3. Add this back to, hey, I didn't have 4 states. How many states did I have for this cycle? 3. You know, we don't have that many cycles in thermo, so we make up some. You can't find this cycle in practice, but you could find it on a lot of thermodynamics exams. That's just like your Calculus 1. How many derivatives do they have of all these functions in your textbook? Thousands. How many do you really need to know as a functioning engineer? A handful. Last time I used the hyperbolic, sinh, cotangent, blah, forget it. Come on now. But every day I use exponential. Every day I use quadratic, simple polynomial, logarithmic. So anyway, so this is made up, but you can analyze it just the same. All right, so you could have 3 states, 3 processes make the cycle, 4 states, 4 processes make the cycle, and then you can continue on. It's just when you start getting 5, it becomes ridiculous. What's the key idea about a cycle, though? Where you begin is where you end. You got to get back to where you started. Constant properties. Sometimes people ask, why is thermodynamics so hard? Well, one reason is, not the only reason, there's vocabulary. And sometimes people are trying to say, what is this? What does this mean? What's the interpretation? Well, here's one that's probably pretty easy. Somebody says the process is isothermal. What does that mean? What does isothermal mean? The property known as temperature is constant during the process. That means T is equal to a constant. let me just get this straight up. There'll be the same mistakes in Thermo 2, right? Q equal to 0. What does that mean? No heat transfer during the process. But this is not the same as being isothermal. This one is called adiabatic. Adiabatic, meaning there's no heat transfer. All right. Sometimes you can have an adiabatic process which is isothermal. Sometimes you can have just the opposite. It's an adiabatic process that's not isothermal, and vice versa. So you have to be careful. A lot of times students will confuse those. Isobaric, take a guess. Constant pressure. Isochoric, take a guess. Constant volume. And they mean the same. Isometric, constant volume. Why do you have different names? Just to confuse? I don't know. I really don't know. But some people claim that the reason that the students throughout the nation, not just at UTSA, have trouble in thermodynamics is because there's so many new words, new terms. All right. So adiabatic, I didn't write up there, but I should have. State postulate. This is something we hit in Chapter 1. And when I teach Thermo 2, I'll be covering something. Somebody will ask me a question, and I'll say, you know what? The answer to that question's back in Chapter 1. Oh, that's so embarrassing to the student, right? What? I passed Thermo 1? I even earned an A. Here I am in Thermo 2, halfway through the semester. I ask you a question. You say, the answer to that's back in Chapter 1. Chapter 1 where they described the state postulate. Huh? Well, okay. The state postulate basically says for the type of fluids and systems that we are interested in, simple compressible systems, simple compressible fluids, the state is completely specified if you can know or determine two independent intensive properties. We already know what a property is. We have some examples of properties, don't we? Is pressure a property? Yeah. Temperature a property? Yeah. Those are our two favorite properties for fixing the state, because temperature and pressure are both intensive properties. So our favorites are temperature and pressure. But any two independent intensive properties for a simple compressible substance or system is necessary and sufficient to determine the state, hence get all the other properties. That seems like that's almost too good to be true. So, this is another keyword though, independent. They have to be independent. Unfortunately, temperature and pressure often are not independent. Let me just give you the bottom line. When there's a two-phase mixture, temperature and pressure are not independent. When something's boiling or condensing, it's not temperature and pressure, not independent. We'll build on that, don't worry. We'll build on it. But often temperature and pressure are independent in the superheated region and subcooled region. All right. Simple compressible, what is that? Well, in the absence, this is like a legal definition. In the absence of electrical, magnetic, gravitational motion, and surface tension effects, the energy is described by just two independent intensive properties. It's a simple compressible system. You're just all of our fluids are simple compressible systems or substances that we deal with in this class. Water behaves that way, air behaves that way, oxygen, ideal gases like oxygen and air and nitrogen, and all our refrigerants that we're very much interested in. Then what's not one that's a simple compressible system? Well, something where you have a lot of electrical contribution to the energy of the system. It has some electric charge associated with it. Or surface tension is one that may appeal to you, where the surface tension effects are significant for the energy. Just know that most of ours are throughout. I can't think of one problem in this class where we're not dealing with a simple compressible system. And again, I often will say system or substance. Okay. It's how energy is manifest in it. Independent properties. If you have a superheated steam, there's the temperature, there's the pressure. I can get the specific volume. I can get the internal energy. I can get the enthalpy. I can get the entropy. Because temperature and pressure are independent, those two fix the state. Boom, I got all the properties. I just have to find the right table. Unfortunately, when you have a two-phase system, where this is vapor up here and that's liquid down there, that's what I'm trying to show with a slightly different color, they're not independent. You have to have more information. Maybe you need to know not just well, first of all, I'm trying to show here is that if it's two-phase, if you know the temperature, the pressure, you just look up. It's not independent. The saturation pressure is not independent. We're going to build on this when we get to PVT surfaces. Dimensions and units. This is a review back to physics. How many fundamental dimensions are there in science and engineering? 7. What are they? Length, mass, time, temperature. Those ones we use a lot. We also use in this class amount of a substance. We don't really use electric current. Every now and then we do, but most of the time not. And we don't use luminous intensity. What are the typical SI units? Meter, kilogram, second, Kelvin, kilomole. What are the symbols? M for meter, kg for kilogram, S for second. K, I know some people put a degree symbol on it, but it's not supposed to have one on there. Every now and then I'll slip and put one on there. It's just Kelvin without a degree symbol on it. What about Celsius? Degree or not on it? It's about 50-50 in the world. Our textbook puts it on. But if you look, there's some places in the world, nope, leave it off. How about Fahrenheit? About 100% of the world that uses Fahrenheit put a degree symbol on F. Okay? Right. Then ampere and candela. And then you have many derived or secondary dimensions. Area is example, density, speed, force, work, power. You can break it down to the primary dimensions like length times length, mass divided by length, or time, length over time, etc. Or you can put it in the typical SI units in the symbols describing that dimension. Like I remember work is a joule is a Newton times a meter. I was teaching Thermal 1 a couple years ago. And it was in chapter 2 where I asked them to calculate some work. No, I asked them to calculate the torque in a shaft. And so, anybody remember units of torque for a rotating shaft? What's the torque in a shaft? SI unit. Isn't it the moment of a force would be the perpendicular distance and then the magnitude of the force? So it'd be like meter Newton. All right? Some students really learned that, hey, I know what a Newton times a meter is. Guess what that is? Joule. So they reported the torque as 50 joules. There it is, professor. I got the calculation, I got the right magnitude, and there's my units. It shocked me, it surprised me. Because nowhere could I ever find in any physics or other book where anybody gave unit of torque as a joule. So when you have torque, the unit of torque is a Newton times a meter times a Newton. But it's never a joule. So I point that out because I was shocked one time when I had to grade exams. Would you have reported units of torque in joules? Good. All right. This is Thermo 1. One slide. If I had to say one slide without a lot of detail, what's thermodynamics? Well, basically mass is conserved, energy is conserved, and energy is always being degraded in processes. So this one's simple, but sometimes we even forget it. Mass is conserved. Sometimes I have a hard time convincing students that's still right. You'll be in senior design, they'll have forgotten it. Yeah, I got a senior design project. We're producing more mass than what? You can't do that. But I have a chemical reaction going on. If they have a chemical reaction, can they then throw out conservation of mass? Nope. But I'm heating it up. I'm heating it up and I'm pressurizing it. Can they throw out conservation of mass? No. Mass is conserved. Only time is when this guy. And we don't want to see a lot of those going off. Uncontrolled weapons. That's nuclear fusion, fission. Okay, in those cases, yes, I agree. You can have a conversion of an itty-bitty amount of mass times a huge number, speed of light squared, and you can make things really hot. And it does happen in power plants, nuclear power plants. That's happening. Slight change of mass, releasing a whole lot of thermal energy. But in conventional mechanical engineering, no, 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 no. And mass is conserved, period. All right, what about energy? Energy is conserved. That's called the first law of thermodynamics. It brings up the interesting notion that there's many different forms of energy, and that's what makes it hard. Energy can be in this form, energy can be in that form, and you can convert between forms, but at the end of the process, it has to have the same total amount of energy as what you began with. So maybe you had a lot of mechanical or thermal energy, but the sum is always the same. You can't just destroy energy. You can't just produce energy. I know we'll use that term, like we're producing energy by drilling a hole in the ground and getting oil out. But that's not producing energy. That's just getting oil and moving it. Then the second law of thermodynamics, that energy is degraded in a process. Think about this. I have a form of energy, it's mechanical. I want to convert it to thermal. Is that hard? Take your hand, rub it together. That's exactly it. Take your hand. If you're doing this, you have mechanical energy. You can take your hand and rub it along the top of the table too. Your temperature sensors in your hand will tell you you can feel the warmth, the increase in temperature. Is that a real increase in temperature? If I get a thermocouple, will I actually detect it? Yes, you will. Where's that temperature? Why is it so hot? It's because of, that spring that you're compressing right there is a good example of not a simple compressible system. You want to hold that up? Show them. And if you actually took that spring and put a thermocouple on it like a rubber band, anybody ever did that with a rubber band? Stretched the rubber band, put it to your lips because you could sense temperature very well with your lips. What do you detect? Let it go back again. The rubber band and that spring is an example of not being the things which the tools that we learned can analyze easily in this class, because the energy is associated with the state of stress in that rubber band or in that spring. So thank you for bringing the demo. All right. That goes back to the other slide that we had. But this one's easy, and you can achieve 100% conversion. You know, you can walk into Walmart and go to any clerk and say, my room is cold. I know that I can purchase some electricity from CPS. Do you have anything that converts energy from the form of electrical to heat? Can you sell me something? What's the Walmart clerk going to do? Come on over. I'm going to show you. We're going to show you a space heater. There you go. Plug it in. Buy electricity. Somebody says to the Walmart clerk heater, my bedroom's hot now. It's summer, not winter. Last winter, you sold me a space heater. Can you sell me something? that will take the heat out of my room. I learned thermodynamics. I know that energy is conserved. And push it back, and so I can push the meter backwards and sell energy, electric energy, back to CPS. I want to have renewable energy straight out of my bedroom. Take that hot energy out of my bedroom and sell it to CPS, and actually it'll be nice and convenient. I can sleep at night because it'll be nice and cool. What's the clerk going to say at Walmart? They helped you in the winter. What are they going to say in the summer? I'll call my manager over or something. Hey, they're going to throw you out. They don't sell anything. That's hard. To burn something, to get it hot, to turn something, to do something useful. Often it's lift a weight in a gravitational field is kind of the benchmark for doing something useful, or turning a shaft is doing something useful. But thermal to mechanical or thermal to electrical, you need to get an engineer. You need to hire an engineer. It's hard. All right. Talk about mass very quickly. A lot of people have water bottles. I usually can find a water bottle. Did you just have a water bottle? No? You have a water bottle right there. There's 2 water bottles. Can you tell me off the label how much water is in that water bottle? Half a liter? How much is in yours?
591.
Oh, it's a little more. Okay. 591 milliliter. So what's that, a quart? I don't remember. Is that 500 milliliter? 500. Everybody picks those up and they have a sense. But every now and then I'll say, tell me how big a kilogram is. I have no idea. How many years you've been making calculations of kilograms in your engineering education? Physics, chemistry. Many. But you have no sense what a kilogram is, right? No, I have no idea. Get a full water bottle, pick it up. I see 1, 2, 3, 4, 5 of them around here. I know that one's a little larger than the 500 milliliter. And how big is, how many kilos is in a water bottle? 1 liter water bottle would be 1 kilo. Half a liter would be half a kilo. So you get a good sense of what a kilogram is. And you pick them up all the time. Pick up a water bottle, 1 liter, there you go, that's a kilo. How about a pound? Pound? That half a liter water bottle is about 1.1 pound. Roughly a pound. A little over. So anyway, I'll ask a question on an exam. Maybe I have it on the next slide. No, I don't. I got rid of it. It's like, I have a half a liter water bottle. What is the mass of water in a full, half a liter water bottle? And then I'll put something like 0.05 kilograms and 0.5 kilograms and 5 kilograms and 50 kilograms and 500 kilograms. And somebody will give me 500 kilograms. And usually they're from some country where that's the common. They're not thinking pounds. And I say, okay, what's your weight? Oh, about 72 kilos. No, 69 kilos. They're struggling with the second significant digit on their weight. And they're telling it to me in kilos. Okay, now let's take a look at the answer you put for this exam question. Oh, 500 kilos, no good. Yeah, of course it's no good. So help yourself every now and then. I challenge you, try to find something that you can relate to and pick it up. It's like, hey, this is half a kilo. Get a full 1 liter water bottle. That's 1 kilogram. All right. That's a true story, not too long ago. Density, we already talked about that. What is it? Mass per unit volume, SI units, kilogram per meter cubed. We like to use the reciprocal of density. We call that specific volume. The specific volume is 1 over the mass density. It's the volume per unit mass. So if somebody said the specific volume was, 0.01 meters cubed per kilogram, right? I'd say, if you give me 1 kilogram of that substance, and it has that specific volume, I'm going to tell you the space it's going to occupy is 0.01 meter cubed. That's all it is. It's the volume occupied by that amount of mass. All right. Now we have the specific weight and the specific gravity. These are two confusing terms. Gamma is often used for specific weight as G for specific gravity. All right? Which one, who wants to volunteer to give me the definition of either one of these? I'll take a volunteer, raise your hand, then you tell me which one you want to define. Who's a eager, okay.
I think specific gravity is gravity, force of gravity with the weight, or not the weight. Never mind.
All right. Very good try. Thank you for trying. How about somebody else, though? You were pretty good. You were on gamma. That's what you were on. You were on G, that's gravity, times rho. What is rho? Mass density. So gamma, the specific weight, is rho times G. All right, let's work out the units on this gamma, this specific weight. What are the units on it? Well, bust it out. Let me get rid of this to make some room. Would it be 9.81 meters per second squared? That I'm leaving off the 9.81 on the G. And then we're going to have, for rho, kilograms per meter cubed. Did I do that right? And that what is a Newton? Is a Newton a kilogram meter per second squared? Is this correct? Do you see what I just did? So that I can cancel the kilogram, cancel the meter, cancel the second squared. What's left over? Is that equal to a Newton per meter cubed? What is a meter cubed? Our typical volume. Meter cubed describes volume, doesn't it? What does Newton describe? Mass? Does Newton describe mass? No, that was kilogram that described mass. What does a Newton describe? Weight. It's weight per unit volume. That's the specific weight. Weight per unit volume. So if somebody says, I'm going to give you, 3 cubic meters of this substance, and the specific weight is 900 newtons per cubic meter, can you tell me how much weight I'm giving you? Yeah. 3 times 900. I'm just making those numbers up. You can't read my 900. There you go, a little better. Okay. Now the hard one. That really, it's easy, but unless you already know the terms and familiar with it, it's like, how did they come up with that name? Don't ask me. It's just the name that's out there. What is the specific gravity? SG is the symbol often used for it. No, good try. That's why it don't make no sense. I'm going to tell you the specific gravity of mercury is 13.6. Is the specific gravity of mercury 13.6? Liquid mercury, is it 13.6? I think it is. What did I just tell you? It's dimensionless. Specific gravity is dimensionless. Does that help? You're on the right track. I know that all I have to do is ask a tough question. Student volunteers to answer it. I belittle them, and that's the end of the semester for them. So I don't want to do that. I don't want to do that. Okay? So let me help you a little bit. Does that jog your memory? The specific gravity is 13.6 for liquid mercury, Hg. How about this? I'm going to work with them just a little bit longer. The specific gravity of H2O is 1.00000. Did that help? I got you too flustered, sorry.
It's the density of a substance over the density of water.
That's it. And that water for benchmark is at a particular temperature and pressure. It's at 1 atm and at 4 degrees C. So this is the density of the material of interest divided by the density of water, at 4 degrees C and 1 ATM. A lot of times it doesn't change much, so you just say liquid water. What's the density of liquid water? Around 1,000 kilograms per meter cubed. But if you want it to 3 or 4 significant digits, it's not precisely 1,000. It's a function of temperature, and we'll talk a little bit more about that. But at 4 degrees C, what's special about water at 4 degrees C? It's its most dense. And as I cool it to go to 3 degrees C and 2 degrees C, 1 degree C, 0 degrees C, what happens to water at 1 ATM at 0 degrees C? It starts to turn into ice, solidify. What happens to water when it solidifies, goes from liquid water? Does it expand, contract? It expands. It's one of these miracles of the universe. Most stuff, when they solidify, go from liquid to solid, contract. Water, just the opposite. It expands. Anyway, so it's 4 degrees C. Molar mass, or another old term, molecular weight. Somebody says, I think I know the molar mass of air. What is the molar mass of air with units? Molar mass of air. What is it? It's a number. What is it? Some are shy. Who wants to take a guess? Just a guess. Okay, give me the molar mass of something else that you may know. How about the molar mass of diatomic nitrogen? The molar mass of diatomic oxygen? The molar mass of monoatomic carbon? 12. 12 what? 1 carbon, 12 what? Grams per mole, or we like to use kilograms per kilomole. That help? Carbon's 12. What was oxygen by itself? O by itself? 16. Diatomic oxygen, what's its molar mass? Because that's the way oxygen floats around in the air that we breathe. It's diatomic, not monoatomic oxygen. It's right at around 32. What? Kilograms per kilomole. What about nitrogen? 14, diatomic, 14, 14, 28 kilograms per kilomole. What about air? It's a mixture of oxygen, nitrogen. It's between 28 and 32, but it's mostly nitrogen. Around 29, 28.97 if you want to throw it out to 4 significant digits, which is a little bit on the ridiculous side. But here, there it is, the 4 significant digits. Dry air, standard dry air. What are the units? Kilograms per kilomole. Meaning, if I say I have 1 kilomole of air in this container, then I could tell you how much mass of air you have in that container. It's around 29 kilograms. Molar volume. Well, we talk about the volume here. We talk about the volume. We talk about the specific volume. What was that? Volume per unit mass. Which one was intensive? Which one was extensive property? Now they have this molar volume. Huh? Well, let's do this. If I said I have this many moles, this is the amount of gas in kilomoles, and I multiply by the molar mass, what do I get? What was the molar mass again? That's how many kilograms per kilomole. What will I get? What's the result of the amount times the molar mass? The mass in kilograms. See that? So we can go back and forth between a mass description of the substance and a molar description of the substance. And I know it's a little tricky, and we do a lot more of it in Thermo 2 than we do in Thermo 1, but we need to be able to do it in Thermo 1. And the thing that bridges the gap is that molar mass. So this is that equation correct? Give me a thumbs up if you like it. Thumbs up? Good? All right. So now we have 2 volumes. And now we can have a third volume, which is called the molar volume, the V bar. What? That's the volume divided by the amount. Instead of dividing by the mass, divide by the amount. And so it's V bar. Okay, so this had to have units of meters cubed per kilomole. Molar volume. Let me do this. How many people have heard of the ideal gas equation? How many people have heard it? Ideal? Professor. No cheat sheet. I'm going to stop, I'm going to pause, I'm going to walk around. From memory, you write down the ideal gas equation. That's not fair. Yes, it is fair. Ideal gas equation. And I want you to define each of the terms in the equation. It's not that hard. Okay? Let me see your ideal gas equation. All right. So the ideal gas equation, PV is equal to nRT. Most people wrote that. Then somebody's P is pressure. V, the volume. N, number of amount, the number of moles or kilomoles, it's the amount. R, gas constant. T, temperature. One correction I'd put to be consistent with the book, I'd put a bar over top of it. All right, so what is our bar? 8.314 kilojoules per kilomole Kelvin. It can also be written 8.314 kilopascal meter cubed per kilomole Kelvin. Both of those will be very useful to you. Might as well just tell you right away. Think about it as your choice. I can put it in kilojoules or I could put it in kilopascal times a meter cube. You know what? It looks like a kilojoule is equal to a kilopascal times a meter cube. Don't matter how many times I say it in Thermo 1. Don't matter how many times I say it in Thermo 2. There'll be somebody always asking me, even late in the semester in Thermo 2, where did that come from? Then I'll re-show it. Do you think you could prove that to yourself? I'd encourage you to do that. Then you internalize it. Then you got to step up. It's not going to trip you up on exams and slow you down. All right. So that's R bar. What's the name of R bar? Universal gas constant. Okay. What about this T? Can I put any T in there? Could I put 20 degrees C in there? Absolutely not. How many people, no matter what I say, how many times I say it, on an exam, I'm grading it, there goes 20 degrees C. What do they need to do? Make sure it's in Kelvin. Convert it to absolute temperature. It has to be an absolute temperature. What about this pressure? Can it be gauge pressure? It must be absolute pressure. Just like T must be absolute. What's the pressure of the air in this room? About 1 atmosphere. About 100 kilopascal. 101.3 kilopascal is a nice number to say, oh, it's atmospheric pressure. But somebody say, well, I don't feel a lot of air pressure. It must be zero. Yeah, it's zero gauge, but it's not zero absolute. This is the volume. That's the amount. True? Somebody says, you know what? I don't like working in amount. I like working in mass. Could I put PV is equal to M? Oh, how did I convert? N times molar mass. Doesn't that give me M? Divide by cap M there to make it consistent. And now this is just RT without the bar. What do you mean R without the T? That's the gas constant for the gas of interest. Not the universal gas constant for any ideal gas, but only for the oxygen if you're using oxygen, or only for the nitrogen if you're using nitrogen, because R is R bar divided by the molar mass of the gas you're using. Make sense? Another version, they say P V over M equal to RT. That's P lowercase v RT. This is a very popular form of the ideal gas equation. What is this lowercase v right there? Specific volume. What is this R? The gas constant for the gas of interest. Makes sense? Somebody says, ha, why don't I do this? Why don't I just say PV divided by N is equal to R bar T? That's equal to PV bar equal to R bar T. You know what? That's a very popular form of the equation too. That makes sense? Do you see the parallel between the two? So we need to be able to do good, jump back and forth between a molar description and a mass description, especially for ideal gases, and use the ideal gas equation. I'm going a little slower than I'd like to. Let me just continue on. I wanted to give you a quiz today, but I'm not going to be able to do that. Zeroth law of thermodynamics. It's so simple, I don't even know why. First of all, they have the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and even the third law of thermodynamics. Which law do you think came first in the history books? Actually, it was something like this was the first. They knew there was a limitation on converting energy between forms, but they really didn't have a firm grasp on energy. But they knew there was limitation. Then they really got, hey, energy is something that's conserved. And then, I can't remember if this one came next, but anyway, it's like this is not the first. By the time they figured out they needed the zeroth law, and the most logical place was before the first and the second, they weren't able to renumber. And so they're stuck with saying, okay, I guess we'll call it the zeroth law. If things keep going, we're going to have a negative one-th law. You know, a couple more years, they'll come up with the negative one-th law. But anyway, the zeroth law just says that if I have an object A and it's in thermal equilibrium with an object B, and then I have an object A in thermal equilibrium with the object C, that somehow, lo and behold, I can now conclude that B and C are in thermal equilibrium, meaning they have the same temperature. You're impressed. I'm glad to see it. They got a long time without knowing this. But then somebody decided they really needed the zeroth law. So there you go. You can learn more about the zeroth law somewhere else. Now we have temperature scales. What does temperature indicate? Somebody says mass indicates, sluggishness to change of the state of motion. What does temperature indicate? How hot it is. That's basically it. How hot it is, how cold it is. So you have temperature scales. You have the Kelvin and you have the Rankine. Those are absolute. You have degrees C, that's Celsius, and Fahrenheit. Those are relative. What do you mean relative? Well, we work with a lot of water in this world. So something special at 0 degrees C and 32 degrees F happens with water. What happens at water? Water freeze. Right? Then what happens at 100 degrees C or 212 F? Water boils at 1 atm pressure. So it's a boiling point. Point of water. Okay. Those are relative to what happens with water. Then you work, and I'm not going to do it now, to an absolute temperature scale. You can work with ideal gas thermometer to build it up. And you find that the Kelvin is the absolute temperature scale for the SI, and the Rankine is the absolute temperature scale for the USCS. And to convert between the two, 273.15, I think, not 14. 273.15. Somebody can double check the fifth digit on that. And is that right? Something's wrong with my memory. It's 0.15, yeah. I don't know why I have a typo there. And then to get from Fahrenheit to Rankine, you add nearly 460. A lot of people, we just forget those last two digits, but if you want to put them in, there you go, put them in. Double check them, put them in. Okay. 273 or 460 is close enough. So you have an absolute temperature of 0. Let me ask you this. Could somebody get a -1 Kelvin temperature? Could it get it so cold? Well, then why would it be 0 absolute? I mean, it seems like absolute 0 means you're not going to get any further cold, right? It's when things have no motion. Even electrons have no motion. You don't easily get to 0 Kelvin. Physicists spend their life trying to get closer and closer. All right. Same thing over here. Can I get -5 degrees Rankine? No, it's impossible. You mean we just haven't achieved it yet, but we can do it someday? No, no, no. It's impossible. All right? Sometimes I've been there and I've seen somebody that'd be doing some senior design project. And we had the temperature and it's going down like this, and it goes from 1,000, it goes to 0, and it goes to -1,000. Oops, I have a question for you. What's your temperature scale? Oh, it's a -1,000. That's our lowest temperature. We calculated it. Our computer program shows us -1,000. What temperature scale you got? Ooh, okay, it can't be Kelvin. Nope, can't be Kelvin. Can't be Rankine. Can it be degrees F? Think about it. What's the absolute lowest temperature in degrees F? Can I get to -470 degrees F? No. All right, can it be -300 degrees C? No. Have you invented a new temperature scale? No. What do you have? An error. That's true. I've seen it, done it. It's like, come on, people. You're finishing. You pass thermodynamics with me. All I can do is hang my head in shame. So this is absolute 0. Now there's something special. -40 has the same hot and cold as -40. What? Yep. -40 degrees C is the same hot and cold as -40 degrees F. It's that cold. It's very cold. I shouldn't say hot and cold. But they have the same temperature coldness. Did you know that? Kind of unique thing. All right. Also, one thing to really point out, that you go from 0 to 100, you go from 32 to 212, that's 180 degrees F change. That's 100 degrees C change. So a change of 100 degrees C is exactly the same as a change of 180 degrees F. Or 1 degree C change is 1.8 degrees F change. All right. 1 degree C change is also 1 Kelvin change. So if you go from 20 to 40, you go from, 293 to 312. It's the same number of temperature increments in degrees C as well as degrees F. This is, put a little star by something like that, because I have to remind students of that too. Like if you got everything in the first lecture of this class, you pretty well got this class. You can just remember it all, right? But you can't remember it all. But I'm trying to help you, like, tuck this away. A change of 1 degree C is 1.8 degrees F. A change of 1 degree C is 1 Kelvin change. And a change of 1 Fahrenheit is exactly 1 Rankine change. All right. And you can't get lower than those temperatures for absolute 0. Pressure, we already talked about. What's pressure? Is it force per unit area? Yeah. So if you wanted to get the force of a gas acting on the face of a piston, get the pressure of the gas at that face of the piston multiplied by the area of the face of the piston, and you have the force. We talk about absolute pressure, atmospheric pressure, and gauge pressure. So just like we have 0 pressure, absolute pressure, that means there's no gas molecules bumping against that surface. Where can we find absolute 0 pressure? Well, really nowhere in the universe, but somewhere really close is in outer space. There's just not many gas molecules floating around in outer space. It's a pretty good vacuum. It's a pretty good vacuum. So we would say that's close enough to round off to say absolute zero pressure. But in this room, we have a lot of gas molecules bouncing around at a pressure which is significant, and we would call it 1 atm, 1 atmosphere pressure. And then I could have a balloon, and I could blow up the balloon, blow it, and it would be higher pressure inside the balloon, or a container having gas or something inside. You can have pressure above, as well as I could maybe have a container and I could draw down and have lower pressure. So you can have what we call a vacuum, lower than atmospheric pressure, or you could have a positive gauge pressure. But this is the atmospheric pressure. What is the atmospheric pressure in PSI? About 14.7. Atmospheric pressure around 14%. Let's round that off to 2 significant digits. Can you round off 14.7 to 2 significant digits? 15 PSI. True? How many people checked the tire pressure in their automobile tires or truck tires within the last year? Every hand goes up, right? What do you have for your tire pressure in your vehicle? 36 PSI. Let's make math easy. Let's say your tire pressure is 30 PSI. Is that a gauge pressure or an absolute pressure for the air in your tire? It's a little hint. You pull out of your pocket something to measure the pressure. What do they call that pencil-like thing? Pressure gauge. So you put that on there. What does it read before you put it on? 0. You put it on and it goes to around 30. Let's say yours is 36. You have performance tires. They're a little bit sportier than most. Most people are around 28 to 30 PSI. True? If you have a truck, how many people have truck tires? 45, 50? 75 even? Yeah, a lot higher. How about semi-tires? Anybody know what the semi-tires run? 120-ish? I don't know. But they're higher. So if your gauge shows you the air pressure inside your tires, 30 PSI gauge, what is the absolute pressure of the air in your tire? 45. And you know how many people will not get that answer correct? It is mind-boggling. The absolute pressure of the air in the tire that reads 30 PSI gauge is 45 PSI absolute. Okay. So, all of this seems so simple, but it's not. How many people heard of the term barometer? How many people heard of the term manometer? Did you know that some people have taught this class at UTSA and they chastise Manteuffel? They say, Manteuffel, you're wasting your time. Everything in chapter 1 is prerequisite material. I go right to chapter 2. If they don't get it, tough. I've been told that. Let me waste my time. How many people heard barometer? All the hands go up. How many people heard of manometer? All the hands go up. Because you have. So, let me do my barometer. You have a test tube. It's a long glass test tube. Test tube is closed at one end, open at the other. I have it. What's filling the test tube if I wave it around in this air right here? What's filling it in this room? Air. All right. I have a vat. This is not good to do if you're doing it physically, but if you're doing it conceptually, it's no problem. I take the vat and I have it filled with liquid mercury. That's why you don't want to, conceptually we can do it, but you don't want to put your hand down. I'm going to put my hand in liquid mercury right a second here, okay? All right, so I take that test tube and I bring it down and I put it just like that. Bring it down. What's inside this test tube right now? Air. Probably liquid mercury goes in a little bit inside. True? Let's say I put it all the way down like this, and maybe right there now is the liquid mercury line. What's all of this right in here in this test tube? Air. Now I take that test tube and I tilt it a little bit and tilt it and I get it just a little bit like this, what happens to the air in the test tube? It's still going to be like this. All the air is trapped down there. No, the air is going to bubble out. What's going to completely fill the test tube? Is there any air in the test tube? Now I tilt the test tube back like this. I kept it completely submerged the whole time. What's in the test tube? Now I raise the test tube like that. When I bring that test tube up, out, sometime it'll get to where there's a level of mercury, but something else is above it. That's not liquid mercury. First of all, when I bring it out just a little bit, what is right up in here? Liquid mercury. But then if I can bring it out, it's like that's liquid mercury, but then it stops, and there's a distinct clear layer. I can see it through the glass test tube. There ain't liquid mercury above it. What's above it? Air. It just happened to get in there. No. But people will tell me air's in there. What's in there? Nothing. Or what's really in there is like outer space, a few molecules floating around of vapor, mercury vapor. But because liquid mercury has such a low vapor pressure at room temperature, you just say nothing. It's close enough to nothing that it exerts no pressure. What's the pressure of the gas up there? Zero pressure. Is that zero pressure gauge or zero pressure absolute? Absolute. Now, how many people know how high that column will be of liquid mercury in that glass barometer? Because couldn't I continue to bring this out? And until I bring the bottom out and let air kind of rush in and the mercury fall out, will the level go up? No. The level will stay right there. What is this height? Who can remember the number for that height? I think I heard the right number. What was it? 760 millimeters. 760 millimeters of mercury. Remember that number? That's a column. And that's a measure of how what does that measure? Okay, let's do this. How many people remember this number in inches of mercury? 28.97 inches of mercury. Anybody listen to the weather? They say, oh, we have a weather front coming in or going out. They said the barometric pressure is 28 point blah, 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 and rising or falling. How many people have ever heard their grandparent or friend or parent, somebody say, ooh, my joints are aching because something's happening in the weather? Or sometimes I'll get a headache because it's like there's higher barometric pressure, something pushing in. Anybody? You're too young, you're too healthy. Just wait. No, talk to your grandmother every now and then. Give her a call. She would love to hear from you. Believe me. You guys think that your grandparents are going to live forever. They're not. And when they pass, you'd regret not calling them. Call them up. Hey, Grandma, how's your joints? Stuff like that. But anyway, this is in the weather reports that you should listen to because they talk about the barometric pressure. So if the barometric pressure goes up, that means the air pushing down on this layer of mercury is going up, meaning the height is going to rise of the liquid mercury in the barometer. And if the pressure is going down, you have a low pressure zone, then the air pressure in that around that zone is less pushing down on that mercury layer. Hence, the height falls a little bit. It's not 760 millimeters or 28.9 inches of mercury. That's a barometer. True? Now we do a manometer. We have a tank, and we want to somehow sense the pressure in this tank. So we come out with a tube. We make it go through a U like this. True? And I fill that tube with some mercury. Where's the mercury going to sit? In the bottom of the tube. True? And then somehow the pressure, the gas pressure in this tank goes up. What's going to happen to the level of the manometer, the fluid in the manometer? One side's going to go down, the other side's going to go up, isn't it? So if the pressure in this tank goes up, and this is open to atmospheric pressure over here, what happens? This one goes down a little, and that goes up. So the new level is here, the new level is there, and now we have a height difference between the two sides. What does that infer? That tells me the gauge pressure inside the tank. So the tank pressure, this is the tank, is equal to the atmospheric pressure, the pressure atmosphere outside, plus whatever fluid I have in my manometer. I could have a mercury-filled manometer or a water-filled manometer times G times the height difference in between the two sides of the manometer. Are you good at manometer problems? Get good, right? Please. Otherwise, you right? You need to be able to make some calculations of pressure variation, and it's very simple. And so our two common fluids are water and mercury. All right. How many people have seen a Borden tube pressure gauge? I used to bring one. I could bring one. I have one in my office. But basically, the air or the fluid comes up and it fills this C-shaped tube, and it fills it. And just like, when you're little and you had that party and you would blow into the thing, it would unravel and then blow out the end, party favors, stuff like that. Well, if the pressure goes up, what does this C shape want to do? Straighten. And what you do is you hook it up to some mechanisms to move the pointer and rotate the pointer. So the pointer will change location as the pressure goes up. That's a Borden tube, named after French engineer Borden. Are these still around, Professor? Yeah, because they don't fail when the electricity fails. And they're pretty robust, and they're pretty cheap, and have a lot of experience manufacturing them. Hydrostatics, we're done for today. I quite didn't finish chapter 1. Please, I do have videos online. You can watch them. I just repeat myself. Thermodynamics hasn't changed. And I'll see you on Thursday. Solve a lot of problems, okay? Read the chapter and solve problems.